In the previous lesson, we saw how a diffraction grating is a screen with multiple equally spaced, equally wide openings that diffract light. We also saw how waves with shorter wavelengths diffract less than waves with longer wavelengths. And we use this phenomenon to separate white light into its component colors. So essentially, a diffraction grating is like Young's double slit experiment setup, but on steroids. In Young's experiment, we saw the light not only bend or diffract to turn into a point source of light, we also saw this light interfere with itself to produce a fringe pattern. So shouldn't the same be happening with a diffraction grating? Shouldn't the light leaving the diffraction grating turn into a point source of light and interfere with itself? Shouldn't we see a fringe pattern here too? Well, as it turns out, that's exactly what happens. In a diffraction grating, the light isn't only breaking to produce different colored lights. It does so in the form of an elaborate fringe pattern. Just like in Young's double slit experiment, the light leaving a diffraction grating also turns into point sources of light at each opening, and then proceeds to move forward and interfere with the waves emanating from other openings. And just like in Young's double slit experiment, the waves create a fringe pattern on the screen at the other end. The only difference is that instead of just white light, each component produces its own diffraction, its own interference, and therefore its own fringe pattern, because each color of light has a slightly different wavelength. You can imagine it like different color waves emanating from different diffraction grating openings, interfering with the other waves of its kind, and then creating a fringe pattern on the other end. Only this is happening for all color waves at the exact same time, but at slightly different angles, because these waves diffract at slightly varying degrees. For example, violet color diffracts the least because it has the shortest wavelength, and red color diffracts the most because it has the longest wavelength. So what you get at the other end is this fringe pattern of rainbow colors repeating again and again, with areas of dark in between. Now these dark areas are the places where destructive interference has occurred for all wavelengths. You can isolate the patterns produced by a particular colored wave by using monochromatic light, which is light of one color, or a laser instead of white light, and you'll see the familiar fringe pattern that you remember from Young's experiment. You can also calculate the angle at which different wavelengths diffract to produce this pattern, which we'll get to later in this video. In white light diffraction, you'll notice that the pattern that forms on the screen starts from the center and spreads out in a repetitive pattern. Now we can track these repetitions in the order that they appear. Starting from the center, we have the zero order, or what we call central maxima. And then there's the first order or first maxima, which is the first time the pattern appears around the center. Then is the second order or second maxima, which would be the repetition on both sides of the center. And the third order or third maxima, and so on. These are called orders of diffraction, and the angles at which they occur are governed by the formulaic relationship d sine theta is equal to n lambda, where d is the slit separation, or the distance between the slits on diffraction grating. Theta is the angle of diffraction of a particular order or maxima. N is the order of diffraction, and lambda is the wavelength of the light being dispersed, or the color being dispersed. Rearranging the equation shows us how the angle of diffraction is related to each of the factors. We can see that the angle of diffraction is directly proportional to the wavelength of light. That is, longer wavelengths mean greater diffraction. We can also see that the size of the slit is related to the angle of diffraction inversely, meaning a smaller slit results in greater diffraction. This is just a confirmation of the properties that we've covered in the previous lesson. So let's do some math. Let's say there's a laser beam passing through a diffraction grating that has 200 lines per millimeter. The resulting diffraction pattern is captured on a screen 2.40 meters away. If the second maxima occurs 1.26 meters from each other, can you figure out the wavelength of the laser light? Now you could pause this video to try out the problem for yourself or continue to see how we solve this. Now in order to solve this problem, we need to first find the angle of diffraction. We do that by simple geometry. Since we know the screen is 2.4 meters away and the second order diffraction lands 0.63 meters above the center. That's half of 1.26 meters from each other. So it's 0.63 meters from the center. We can then calculate the angle assuming a right angle triangle. And the simple formula is tan theta is equal to opposite upon adjacent to solve for this. When you do that math, this comes out to 14.7 degrees. With this information, we can plug in the values into our order of diffraction equation, which is d sine theta is equal to n lambda, and solve for the wavelength. So with a little clever trigonometry and our equation, we can easily determine the wavelength of any monochromatic source of light. This can be super helpful in choosing the right wavelength of light for other experiments or determining the wavelength of light given off by elements to develop sensitive measuring devices. Another neat thing about this equation is that we can use it to determine the maximum number of order of diffraction that the light of any wavelength can have once it passes through a particular diffraction grating. Now this particular relationship is governed by a derived version of our equation, and it looks something like this. When n max is less than or equal to d over lambda, where n max is the maximum order of diffraction that can be achieved, and it must be a positive integer. D is the slit separation, and lambda is the wavelength of light used. So in our example, if we were to determine the maximum order of diffraction that can be achieved by our setup, we simply plug in the information and solve for n max, which by the way comes out to 7.9. Therefore, looking at that fact that n max has to be an integer and less than 7.9, the maximum order of diffraction that can be achieved by light of this particular wavelength of 634 nanometers passing through a diffraction grating that has 200 slits per millimeter is 7. And because the highest possible integer that's below 7.9 is 7. And now you know the inner workings of a spectrometer and a spectrophotometer. As we've discussed in our previous lesson, light diffraction and its properties are immensely useful in these instruments. It's only because of a knowledge of how light diffracts and the formulaic relationships it has between these properties that we are able to use them to determine the chemical composition of things. Everyone from doctors to archaeologists to astronomers use these instruments in their everyday work. And I'll catch you in the next lesson.